Welcome to our day 17 notes. I hope these videos are going well for you. Today we have a long list of just kind of examples of all different arrangements of exponential and log equations. So we're going to use the last 2 days of notes, or I guess 3 days of notes, the exponentials, log properties, and then yesterday's notes, which was about combining and separating logs. And we're going to apply anything that we can to try and solve for x. Now, 2 new properties that are not really something revolutionary, but very helpful to know that you can do these things, is if you've got an equation already 2 sides equal to each other equation, you can apply the log of both sides. So it's just basically telling you you're allowed to do that. Just like any other operation, you can square both sides, square root both sides, log will work the same way. Now on here, you do get to choose the base. So remember what I said about the change of base formula last time. If you're working with your calculator, which we will be today, so pause and get one if you need it. Your calculator only has a button for log base 10 and log base e, so that's primarily what we're going to choose. But if there was some way for us to solve it by hand by choosing a different log, maybe that's the route you want to go. The second property is telling you that if you saw an equation that had 2 logs already in it, where their bases matched, and note that there's only 1 log on each side, so it's kind of like the exponential equations section, then their inputs match. So it's very similar to what we did with exponential equations before. We were trying to get the bases to match, have one exponential expression on either side, and if those are true, then you can set their exponents equal to each other. So these are just helpful things to know that you can do them in order to help you to solve the equations. Now let's look at our first one. This is just an exponential equation. So if you can find a number that both 3 and 7 can be substituted for, and the bases will match, then you can solve it using the exponential techniques that we did on, I think that was day 14, the exponential equations unit. But sometimes it's a little bit faster not to find something that they can both become, but just to take the log of both sides. That's my favorite way to do it because it's pretty straightforward and quick and easy. Now, the reason we want to do that is because of that property that we talked about last set of notes on day 16. I'm trying to get that x out of the exponent. I have to be able to access it. And if I take the log of both sides, it looks like I'm almost making it more complicated. Okay, that x is getting further and further away from being by itself. Now we've applied something else. But there was a property on the last set of notes that said that if you've got a log and it has an exponent on its input, that exponent can be moved out front as a coefficient. And that is the magic that takes the x out of the log and makes it more accessible to us. Now there's only one step left to try and get the x by itself, and that's to divide both sides by log of 3. Remember, log is kind of like a function, or it is a function, but it's just a number. Log base 3 is a number. I could type it into my calculator and get a number out. So it's basically a coefficient by the x. And just like if it was any other number, if it was just a 3, you would divide both sides by that number. So that's what we're doing here. Now, if I wanted exact answers, this would be it. Stop right there. That's exact. Doesn't need any rounding. However, in our application problems that we're going to do next class, you are going to want to round these. So let's go ahead and practice typing them in. Remember, log by itself, that button's down here underneath x squared. That's our log base 10. So I'm just going to type in log of 7 divided by log of 3 and get a decimal estimate. Now, what does it say? Round to 4 decimal places, so we're going to cut it off there. Now, if you want to practice this technique, see if you can try example 2 using what we just talked about. Otherwise, keep watching. I'm going to use the same exact approach. I need to first get rid of this coefficient here because I wanted just 2 to the x to be able to remove the exponent x. If I gathered these into one log, then I can't take the x out right away because x is not acting on 5. So first thing I'm going to do is kind of set it up so that it looks like the previous equation. There we go. So a base power of x equals a number. Now, I'm going to take log of both sides from here and pretty much follow through the rest of the steps exactly the same as we did on the last one. And again, we're just trying to get a decimal estimate for that. So typing that into the calculator, log of 3/5 divided by log of 2. Okay, so I said there was a second approach that you could take to this. Second approach would be to go ahead and take the log of both sides right at the beginning. You'll get something that looks slightly different but actually represents the same number. We'll have log of 5 times 2x, log of 3. Now we can use one of the properties that we talked about yesterday in the notes, which was that if you've got something that's being multiplied in your input, you can split that into the sum of logs. And again, the reason I need to do that is because right now, if I took that x out, I'm implying that the x was acting on the 5 when it really wasn't. All right, so in the next step, I'm going to move this log of 5 to the other side and take the x down. And then finally, to get rid of the x, or to get the x by itself, we're going to divide by the log of 2. So that looks very different when we go to put it into the calculator. But remember, the division that we had here, 3/5, is actually the same as these two logs subtracted if you use those properties from yesterday. And I got the same answer as before. Now, while I'm here, I want to comment on something that's probably going through your head, or you might have done if you were trying these out without the video, and that is, why don't we just change these equations into log expressions? We did that in the notes at the very beginning when we first talked about logs. I just rewrote this as log base 3 of 7 equals x. That seems easy enough. Just plug that into your calculator. Well, you could, if your calculator could handle different bases. Now again, the class calculators won't, so even if your personal one does, I would avoid using it unless you know how to handle this when you don't have it there. I don't want it to become a crutch that hurts. But if you go this route, you could also just use log base change formula. Log base change formula allows you to change that base to a 10 or an e. So log over log. And remember, the base of the original one goes in the base of the fraction, so log base or log of 3. And the input goes back on top. So you could just type that into your calculator instead. Let's try that and make sure it comes out to be the same. Log of 7 divided by log of 3. 1.7712. That matches, actually, it's exactly the same problem that I had before. So that's another route you can go. Just make sure you know that if you get to class and you're using one of my calculators, which I will have you guys doing, that you will not have that log base change function available to you. Example 3 is our next problem. So once again, we've got x's that are in the exponents, so I'm not able to just simply move things around and get x by itself. I also noticed that 2 and 5, again, don't have a common power, so I can't really change 2 and 5 and exchange them for different bases to set the exponents equal like we did in the exponential unit. So instead, we're going to do the log of both sides. And since I have no coefficients, I don't have to worry about moving anything over like I did example 2. So I'm just going to straight take the log of both sides right at the beginning. And this allows me to pull those exponents down as coefficients. Now notice that here my exponent is a binomial, and that binomial is the coefficient of log of 2, which means we have kind of a distribution situation. You don't want to leave those parentheses off, because then it'll look like you only multiplied the log to the 1. All right, so now I'm trying to think ahead, kind of plan my next moves. I want to get the x by itself, but right now it's attached to the log on both sides. So one thing that I see a lot of people want to do right away is just divide away one of the logs. And you can do that. It's not going to cause any problems. It just takes up a little bit more space as you go forward, because even if I divide both sides by a log of 2, let's say that's the one I do, I still have an x on both sides. and somehow I have to get rid of this log 5. I can't get rid of both on both sides unless they were equal and they divided away. So one of the sides is still going to need to be distributed to the logs. And at that point, if you've divided by log of 2 on both sides, then you're dividing or you're distributing through a fraction. I don't like working with fractions if I have a way around it, at least not until the very end. It's also going to take up a lot of space when you go to write it. So first, instead, I'm just going to distribute both sides and then start moving things around rather than dividing and then having to distribute anyway. So here we've got x log 2 minus 1 log 2 equals 2x log of 5 plus 3 log of 5. Now everything's kind of free to move around. We don't have any limitations anymore. Nothing is waiting to be detached from something else. And I'm trying to get the x's together so that I can, solve for x. So I'm going to move either this to this side or this one to this side. Doesn't really matter whichever way you want to go. I'm going to move the x's to the left, other logs, constants to the right, just because we're used to seeing x on the left. All right, so now the x's are on one side, but they still have coefficients attached to them. So if you notice, both of these terms have an x. We can factor the x out, and that basically gathers all the x's into a single occurrence of x. It also leaves behind a coefficient that's a constant. It doesn't have any variables in it. So then last thing is to just divide away this entire coefficient, really large, but it's all just one number. And now I've got x by itself, and this is what x is equal to. So that's a monster, but we're not going to calculate it by hand, so it's not a big deal. I'm just going to type that into the calculator. Now do this carefully if you want to do this all in one step, because you do need parentheses around the top and around the bottom in order for it to do that sum and difference in the correct order. Or you could do this in multiple steps and just kind of piece it together. So there's my parentheses around the top. Divide that. And there's parentheses around the bottom, in case you can't see. So x is approximately negative 2.1861. Example number 4 is very similar to example number 3 in that it has a binomial exponent. So we're going to have the same situation where that x is kind of tucked inside of a binomial and we have to distribute through the coefficient in order to get it out and be able to move the different parts around. So I'm going to do that same thing here. Just go ahead and take the log of both sides right away. And again, the reason we're doing that is not arbitrary. It's because of that property that allows us to move the exponent down as a coefficient. It's just making the x more accessible, since that's the entire goal of these, is just do whatever you can to get the x by itself. All right, so again, I want to get to that x, but right now it's attached to this log of 4 and that negative 1. So to help, I'm going to do the same approach that I did on the last problem, which was to distribute that log through, which allows the pieces of this equation to move around better. So now I can isolate the x by moving that log of 4 to the other side. And then finally, just getting rid of everything around the x, since that 2 and log 4 count as a coefficient. So x is equal to all of this. That would be my exact answer. But since we are rounding, I'm going to go ahead and throw this in the calculator. We've got log, and again, I want parentheses around the top so that it does that addition before it starts to divide. So log of 27 plus log of 4, close those parentheses, divided by 2 log 4. So about 1.6887. Example 5 again is another really close match to this type of problem. It really combines what we just did in example 4 with something like example 2 where you've got some extra coefficients floating around. So if you want to try example 5 on your own, that would be another good place to pause the video and try something out. Otherwise, keep on watching. All right, here's example 5. It's like a combination of example 4 where we've got the binomial coefficient or exponent on one side, and also like example 2 where we had the extra coefficient out front. So I'm going to start by treating it kind of like example 2, moving everything else to the other side so all we have is a base with its exponent. Once we do that, it'll look like example 4 and we can proceed just like we did in example 4. So first moving the 142 to the other side, and then dividing away the 2 out front. Next, now that it looks like example 4, we'll take the log of both sides. And after that, we can take the coefficient or the exponent and turn it into a coefficient. Now this time around, I'm going to simplify this a little differently than what I did with example 4, even though we're looking at a problem that's the same pattern as example 4. This is just a different approach that you can take to problems like this. Now this only really works well on problems that only have that binomial exponent on one side. I mentioned it when we were talking about example 3, but I said there that this wouldn't work very well, and that is dividing away the log instead of distributing it in to the x. Now it didn't work very well on example 3 because then I'd have a fraction of logs and still have to somehow distribute it to the x, which just makes it more, just more cluttered to write. There's nothing wrong with it, it's not mathematically wrong. But in this case, since I don't have an x on the right-hand side, I won't need to distribute anything, so there's no harm at all in making that fraction on the right-hand side. You could proceed exactly the same as example 4, or you could take this approach instead. This would also have worked on example 4. So we've got 3x minus 1 equals this big old number over here. And last thing to do is just get the x by itself by moving the 1 and dividing by 3. All of that divided by 3. Now when you go to type this in your calculator, if you want to do it all at once, I recommend putting parentheses around this, and then also definitely around the numerator. I don't know that you'll need, I don't think you'll need the ones around the fraction. I just like to do that just in case, because sometimes my calculator does things in a different order of operations. I know for sure you'll need the ones around the numerator because otherwise it'll divide first before adding. So numerator, fraction, log of 71 divided by log of 15, fraction, plus 1, close the numerator, divide by 3. You can also do this in smaller chunks if you're not comfortable doing it all at once, but I want to make sure if you go to type it in all at once that you're typing it in correctly. So approximately 0.8580. Example 6 is our next one. This one more closely resembles example 3 again because we've got two terms that have binomial exponents. So the first thing that I see to do is probably to split and put this 3 on the other side. One reason I may want to do that instead of just leaving it as it is that if you remember from our last set of notes, if I took the log of both sides, I'd have a log with a difference in the input. We didn't really have a property for splitting that apart, so it's actually going to put me in a pretty bad place. I won't be able to take these exponents out as long as I can't split that input. So I really want to move the 3 first for sure. After that, we're going to have to make a couple more decisions about what the best next step would be. All right, so then also looking back at our last couple of examples, when we were looking at example 5 and we had that extra coefficient out front, the first thing that I suggested was dividing it away because we had a number on the other side. Well, in this case, dividing it isn't really going to get rid of it. It's just moving the problem to the other side. If I took the log of both sides right now, I've got a product here. If I divided the 4 and I take the log of both sides, now I've got a quotient. It's really going to be the same thing because either way you'll have to split that log either into a sum or a difference. So it really doesn't matter, but the point is dividing it is not going to solve anything like it did in example 5. So I'm just going to leave it where it is. Take a step out of my work. Let's go ahead and take the log of both sides then. So now it's going to look very similar to example 3. The main difference being we have a log with a product inside. So I can't right away, sorry for that video shake, I can't right away take that power down, just like I was talking about with example, which one? Example 2, I think. One of those first ones. We weren't able to take that 2x minus 1 down right away because it's not affecting the 4 right now. So I have to split it first to be able to remove that power. Everything I'm doing has a specific reason. It's not just arbitrary. So now that we split that, I can finally move that exponent down since it's affecting the entire input. So our next step is going to be to take both of those exponents down. Okay, and then just like in example 3, I was telling you guys that it's not really beneficial to divide away one of those logs because all it does is creates a fraction on a different term. So instead of creating that fraction, I'm going to approach this the same way I did example 3, which was to distribute the logs through and then gather every term that has an x together and every term that is constant to the other side. The only difference between this one and example 3 at this stage is that we have this extra constant term, so there will just be 3 on the other side. Give yourself lots of space. There's going to be a lot of log terms to write here. Oops, I forgot my 2x. That's pretty important. All right, so now that I've distributed that through, we've got a bunch of individual terms that can freely move around the equation. I'm going to gather everything that has an x in it to one side and every constant to the other. So the 2x I'll leave over here, move the 4x to the left, and then everything else gets pushed to the right. All right, now just like example 3, because I've gathered those terms with the x's to one side, I'm going to go ahead and factor the x out. That finally releases it. It's no longer attached to any numbers. And that represents the right-hand side. Now, to get the x by itself, all I need to do is take that coefficient and divide it away on both sides. So x equals all of the right side divided by all of that coefficient on the left side. Now, once again, if you're typing this into your calculator all at once, instead of doing the numerator and then separately the denominator, you will want parentheses around top and bottom so it doesn't do that division right in the middle of the order of operations. It will take your order and put it literally left to right. Okay, so typing this in, I've got 5 log 3, got my extra parentheses around the top, minus log 4, plus log 6, close the top, all that divided by the bottom. Approximately negative 7.2738. All right, last one for the front side. And this looks very similar to number 2 again. We've got a coefficient in front, we've got a base, a power on one side, and then a whole number on the other side. Very, very similar. Now here the main difference is that our base is e, it's not a whole number. So we're going to use natural log to help us to make this super quick and easy. So first I'm going to get rid of that 3 out front, divide it away from both sides. That was something we talked about in example 5. And it works in this case because I only have an exponential on one side. So kind of like what I was talking about on example 6. All right, now when we take the log of both sides, you can certainly take the log base 10. Feel free to do that. You can take log base 10 every single time, but there's a little bit of a shortcut if you were to take the log base e of both sides, because when I take the log base e and the exponent's base is e, and there was a property 2 days ago in the notes where if the base of the log matches the base of the input, that whole thing is just equal to the exponent. So this whole side is just 2x minus 1. Another way to get that exact same expression would be to go back to this step and just change it. It's exponential right now, rewrite it as a log. So it's gonna have a base e. It's gonna, oh, I'm running out of space here. Okay, so if I do like log roll, log base e of 4, that's this part, equals 2x minus 1. So that'll just kind of skip a step there, but gets you the same exact place. Now, all we have to do is move the 1 and divide by 2 and we're done. So as you can see, it's way easier if the base of your exponential equation matches a base of a log that we like to use in our calculator. All right, so now just typing all of that in. We've got natural log, which is the button right beneath log, plus 1 divided by 2, about 1.1931. For this, I'm going to finally be using the second property that we had on the front page. So that was that if you're presented with logs, as long as their bases match and you only have one log on both sides, then their inputs are equal to each other. So the good news is here we've got bases that match, but I can't just set their inputs equal to each other because I've got this extra 2 out front. So using one of the properties from the previous notes, we're going to move that 2 so that it's an exponent. That way we really do only have 2 logs with their inputs contained. And now, since the bases match and we've got just 2 logs, we can just go ahead and set their inputs equal to each other. You want every step that you do to be reversible, so make sure that I could go backwards by taking the log of both sides, and it's equal to what I had before. So now we're just solving for x, square root both sides. Remember, square rooting both sides means you have a plus and a minus, but log inputs can only be positive. So go back and check what your input was in the original equation. Our original input was just x, so x can only be positive. That means our final answer is just x equals 2 because our domain can only be positive. Example 9 looks pretty straightforward enough, right? It's got 2 exponential terms in it, so why don't we treat it exactly like the front side? Well, the first thing you're probably thinking if you're going to take the log of both sides is that you need to get the 3 to the other side or get the 9 to the other side, because one of the things we talked about with example 6 was that if you take the log right away, you've got the subtraction on the inside, so we had to move it away for that to work out. So if we move that 3x to the other side, maybe I'll move the 6 at the same time. Why not? And now take the log of both sides. Now we still have that problem. I'm still kind of stuck because I've got a sum, or if I had left the 6 over here, I would have had a difference on the inside. We don't have a way to split that apart any further, and I really do need to split it because I need that x to not be inside the log. And the only way to do that is for the x to come out front, and the only way for that to happen is if the x was acting on the entire input. But right now the x is only attached to the 3, so I can't take it out. It's kind of glued there. That means this approach doesn't quite work in this case. And the whole reason it doesn't work and something to look out for is because we have this addition or subtraction of a constant term. If you look back at our examples from the front side, we didn't have anything like that. We only had coefficients that are being multiplied. So instead of taking the log approach, I'm going to revert back to the previous lesson where we were solving exponential equations, and that was to get the bases to match. If that's ever possible, that's totally a way you can solve it, even the problems on the front side. So I noticed that 9 can be turned into a base of 3 because 9 is equal to 3 squared. So this time I could actually use the old base change method we did before. I'm going to go ahead and do that. 9 is going to become 3 squared. It had an exponent of x, so that's still there. Now this is 3 to the 2x minus 3 to the x minus 6. Now we've seen something similar to this before where we had multiple terms with x's in it, but in that case they all had the same base, so we were able to just set those exponents equal to each other and it turned out to be quadratic. That was something that we saw on the last quiz and one of those review questions that I gave you. This does still kind of remind me of something quadratic potentially, but they don't all have the same base, and there's not a power of 3 that would give me 6, so I'm not able to solve it exactly that way. One thing that I know is a power rule. 3 to the 2x is the same as 3x squared because you multiply those powers. So this is like 3x times 3x. Let's do 3 to the x squared minus 3 to the x minus a constant. Now that looks even more quadratic. It's something squared plus or minus that same thing. So this is like your x squared minus x minus a constant. One easy way to do this is to use substitution. We did this before in a previous lesson when we had trig equations. We had something that was squared plus that same thing, and I used substitution to take out the thing, that 3x, that was making it look more complicated than it was, and it makes it look more familiar like a quadratic. So I'm going to use substitution with a different letter, something that's going to stand out and remind me that I need to substitute it back in. In this case I'm going to use a, just because we don't have any a's here. A is going to be that 3 to the x that repeated itself. That's the x in the quadratics. So this will be a squared minus a minus 6. It's factorable. Yep. All right, so now we've got two separate equations that we can solve. So our first equation is a, which was 3x, or 3 to the x, minus 3 equals 0. All right, so the reason this helped out, especially in this case, was that we've got an exponential equation where the bases match, so the exponents must be equal. So our first solution is x equals 1. The second one, which was a, 3 to the x, plus 2 equals 0. Since the bases don't match, we could solve this using logs. But look, we have a log of a -2, and I just said in the last problem you couldn't have logs of negatives, so this one doesn't give us a solution. We only have one real solution for this. Now the whole reason I did the factoring, if we go back and look, why did we do that extra work there? By factoring it, I'm creating an equation that only has a single x, rather than multiple occurrences of x, where I'm trying to somehow group them and extract the x from that group. By separating it, we made them into smaller equations that we actually knew how to handle, and that gave us the opportunity to solve for x. So this one only gave one solution. Our next example is another quadratic. In this case, it's more obvious that it's quadratic, since we actually have an x squared, an x, and then a constant term. But there's also something kind of in there mixed in that I want to take a look at. Besides just the x squared, the quadratic, we also have these e to the x. But the good news is there's one in every term. If you have the same thing in every single term, you can factor it out. So that's what I'm going to do. First, take out an e to the x from all of those. What's left behind is a quadratic. So I know how to handle that. And if you remember that by taking something out as a factor, we have two factors set equal to 0. And just like any other time we factored, including the last one, you can set each factor individually equal to 0 to solve. So that's going to give me one problem that's a little bit simple to solve, and then one that is quadratic. If that quadratic was factorable, I'd break that down again. Since it's still equal to 0, I could then set each of those factors equal to 0. However, this one's not, so to solve it, we're going to use quadratic formula, or you could use completing the square if you like. First, I'm going to turn my attention to this guy. E to the x equals 0. So that's an exponential equation with a y value or output of 0. But if you recall, our exponential equations had an asymptote. Oops, there's my drawing. An asymptote at 0. So they look something like this. Well, if they can never equal 0, then that means this term right here just doesn't give us any solutions. So even though there was an exponential there, we didn't really need it. It didn't provide anything. It couldn't be the reason the equation was 0. So instead we're going to turn our attention to this. And like I said, since it's not factorable, I'm going to use quadratic formula. B squared minus 4ac over 2a. Nine plus 12. And I guess the directions on the front side said that we could round, so let's go ahead and just type that in and round to 4 places. So 3 plus square root of 21 divided by 2. There's our first solution, and then same thing, but minus. There's our second solution, rounded. So approximately 3.7913, or negative 0.7913. All right, so looking at example 11, here's our third situation that's quadratic. And again, I can tell that it's quadratic because of what we talked about with example 9, that e to the 2x, because of exponent properties, that's actually e, or it's not actually as if this is the only thing it's equal to, but it's another way to rewrite that expression, is e to the x squared. The reason I'd want to do that is because here's that thing squared. The next term has that same thing, so this is like x squared and x and then a constant. If I treat it like that, then it's actually quadratic. And just like in example 9, I'm going to use substitution to make it look even more quadratic and make the factoring more obvious or easier because you can see it better. So in this case, my substitution is for the e to the x, because I want to turn that into something that's easier to factor, a term squared. Oops, a. And then from there, we could either use quadratic formula or factor it, depending on whether it is factorable or whether you recognize that it's factorable. This one. All right, so then we can set each factor equal to 0. In this case, I'm going to change it back to e to the x. So e to the x minus 5 equals 0, and e to the x plus 1 equals 0. Basically, it just split our terms where we had more than one term with an e to the x, but I'm still not able to take the log of both sides because of this extra constant. If we didn't have that, we could solve it like we did on the front side. But because of that, this is the best way to get them separated, so you only have a single e to the x per equation. You can treat them separately. All right, and once again, even just looking back at that sketch that I had a few seconds ago, an exponential equation has an asymptote at 0, so it's not able to become negative. It can't cross that, so this just doesn't give us a solution. Over here, we can do this. I'm going to do this by changing it to a log base e, so just rolling the log, natural log, or log base e, of 5 equals x. And now that's my solution for x. But since we're rounding, I'm going to go ahead and type that into the calculator and round it, about 1.6094. Example 12 provides us with a really strange issue. First, I have two terms with the power x and a constant. So immediately I know, unfortunately, we're not back to the simple days of the front side of the notes where I could just take the log of both sides. Again, the problem was that I've got this difference in here, and a log can't be split up once the input has a difference or sum inside of it. So I don't want to do that. but it's not quadratic either because we don't have that power of 2 like we did in the previous ones. In fact, I have a power of negative x. So a lot of people's first instinct is going to be to get rid of that negative, and a negative exponent just means that that term belongs in the bottom of the fraction. But this actually introduces all new problems. It's still not quadratic, can't take the log of both sides. I don't know how I could isolate the x. I mean, I could move 5 over and see what happens. But then I've still got 2 separate terms with a sum in the middle. Yeah, this isn't really working out very well. So let's be a little bit more creative and think about what can we do besides moving that to the bottom to try and get rid of that negative exponent. One thing that will seem obvious once you see it, but may not be that obvious at first, is that with any equation in algebra, you can apply any operation to both sides as long as you do that same thing. So one option I have here to get rid of that negative exponent is to multiply both sides by something that has a base of e that would get rid of a negative. So some kind of higher power than negative x, because once you multiply two things that have the same base, you add their exponents. So I'm going to add two things to get rid of that negative. Now, one thing that might help out if we plan ahead a little bit is multiplying by e to the x, because it gets rid of this guy. Since their powers would be 0, it'll introduce an e to the x here, which is okay because I had other problems like that, and it creates the e to the x squared. It'll become quadratic after we do that. So let's go ahead and try that and see what happens. I'm going to multiply both sides by e to the x. Now, of course, on the right-hand side, that's just 0, since anything times 0 is 0, so it doesn't really affect the right-hand side, which is also good. I don't want to introduce more terms with e to the x in it. Now, this is going to be 6e to the power of x plus negative x. And then the 5 didn't have an e to the x before, but now it does. And then this is e to the x plus x, since you add their powers when you multiply like bases. So now I've got 6e to the 0, which is just 1, so that's a 6. 6 times 1, minus 5e to the x, plus e to the 2x, which is the same as e to the x squared. All right, so now we've set it up so it's quadratic. At this point, if you want to try one of these on your own, I would suggest pausing the video here, because all the rest of the steps I'm going to do will look very similar to example 11. I'm going to apply a substitution here so that it looks more quadratic. I'm also going to rearrange it so it's back in standard form, because I just like to factor with it in standard form. I know I could probably do it backwards, but I don't want to. All right, and this is factorable. All right, so setting both of these equations equal to 0 like we've done in the last couple of examples, that's e to the x minus 3 equals 0, and e to the x minus 2 equals 0. The main difference here is that when you go to solve these for e to the x, you'll see that both equations actually work this time, unlike the last example where we had one that wasn't really a solution. So we're just going to have two answers. That's the only difference. From here, we're going to change that to a log, so that's natural log of 3 equals x, and natural log of 2 equals x. Again, I'm rolling the log, just rewriting it. And we've got our two solutions. Those are the exact answers. Or, if you need them to be rounded, here's our rounded answers. There you go. So natural log of 3 is about 1.0986. And natural log of 2 is approximately 0.6931. Our next example is taking us back to our logs. Let me get this paper folded. So this is going to look more like example 8 in that we're working with log bases instead of exponentials. And you'll see that we have a quadratic again. Now, if you have a log equation where there's only a log on one side, probably the fastest way to handle this is to change it to an exponential. Just rewrite it. Especially helpful if the x is in the input, because then it's going to end up on one side by itself. So it doesn't create an exponent with an x in it. It also will accomplish getting rid of the log. The only other way to do this would be to somehow write this side as a log with a base 3, but that's a little bit tricky. So I'm going to rewrite this. 3 squared equals the input. All right, and since it's quadratic and I want to solve it as a quadratic, I'm going to need to move this 3 squared to the other side, because you can't solve a quadratic if it's not equal to 0, at least not by factoring or quadratic formula. So moving that to the other side, we've got 0, and then -7 minus 9. All right, so that's again factorable. And we can set each of those factors equal to 0. So my two solutions look like -8 and 2, but pause. Don't get too far ahead of yourself. Remember one of the things that I said on the example 8. Here's that again. I said, look, logs can't take inputs that are smaller or that are negative or 0. They need to be positive. So we just kind of scrapped that -2 as a solution because it didn't fit into the log. We have the same situation here, but not the same input. My log has this really complicated input, and remember the input overall, this kind of goes back to when we were finding the domain of logs a couple class periods ago, that whole input has to be greater than 0. Not just x, but the x squared plus 6 minus 7 must be greater than 0. So what we have to do, instead of just saying, oh, that one doesn't work, I need to test them. I need to check if they work, because that input is more complicated than just an x. So to check it, you're going to put in the x into the input, and then make sure that it causes the input to be positive. Is it going to allow our log to be calculated? So I'm going to go ahead and put in the -8, which appears to not work at first glance. But by my tone of voice, you can tell it actually works. Because 64 minus 48 minus 7 is 9. That's doable. So even though the x value was negative, the log still had a positive input, which means this is still a true statement. So it's okay, it works. But I needed to check to be able to tell, because otherwise you might have just crossed it off and dismissed it as not working. And also sometimes, depending on whether your x squared is negative or not, maybe the 2 wouldn't have worked. Maybe that would have caused a problem. So let's just double check that just for good measure, even though it's positive, so it appears to be fine. Ooh, or maybe your c was too big. Maybe that number would have overdone the first 2 terms and then it wouldn't have actually worked. In this case it does, but just be careful with that. They both work, so they're both solutions. All right, last 3, we're in the home stretch. Example 14, this one's also dealing with logs. So the way we've handled logs in the last two times we've seen them was if they have the same base, we set them equal to each other. And then we could just ignore the log part of it and kind of extract the inputs. The second way was if you only had a log on one side, change it back to an exponential. That's quick. So here I have kind of neither situation again. We do have 2 logs, but they're not by themselves. And if I try to move one of these logs to the other side, it still wouldn't be by itself because we've got that +1 over there. So I wouldn't be able to just set their inputs equal to each other. It doesn't quite fit that property. I also have more than one log, so I can't change it to an exponential at this point. So instead, let's go back to our other properties and see what we can do to combine this maybe into a single log. One of our properties that we talked about before was that if 2 logs are being added, you can actually combine them together. If I combine them, then it should look like example 13. So that seems to be kind of a route I want to take. So if, in order to combine them, their bases have to be the same, check. And then when you combine them, their inputs get multiplied. So we've got x plus 2 times 1 minus x as the input for that log. That's okay, that'll work. That looks very similar to example 13. It's got a quadratic input and a log only on one side. So multiplying that, we've got -x squared minus x plus 2. And just like in example 13, basically I'm going to solve this exactly the same way from here on out. I'm going to change this to exponential since we only have a log on one side. So that's 2 to the power of 1 equals the input. So with any quadratic, I want to move everything to the same side and get 0 on the other side. I'm actually going to change these to positive, just divide away the negative, and factor. All right, so once again, with our multiple solutions, basically, even if you had one solution, you do want to check it and test that it works in your logs. Now we have two separate log inputs. We need to check in both of those, whether these x's fit the domains of each of these logs. So remember, this one requires that the input x plus 2 has to be greater than 0, and this one requires that the input 1 minus x has to be greater than 0. So I need to check in both of those. If I plug in a 0 to the first one, I get 0 plus 2, which is bigger than 0, so that works. And then checking it in the second one, 1 minus 0, is 1, which is bigger than 0, so that one also works. And then checking our second solution, negative 1 plus 2 is 1, so that'll work. And we have 1 minus negative 1, which is 2, which also works. So again, both our solutions work, but don't think they always will. Sometimes they won't, so you definitely want to check them. On to our last two examples. Here again, we've got, let me get this in focus, there we go. We've got two logs on one side, and again, I can't just move one to the other side and set the inputs equal to each other because we've got this 1/2 here kind of in our way. So I'm going to kind of do this exactly the same way I did on the last example. Combine these two into one log, then change it to an exponential, and then solve for x. So again, this is a good place to pause if you want to practice that skill, and then join me again to see how it goes. All right, so combining these together, we've got x times x minus 1 as our input. Change this to an exponential equation. A power of 1/2 is a square root. And again, if we're going to solve it, whether it's factoring, quadratic formula, whatever, we need a 0 on the one side. This one is factorable. All right, and once again, I need to check my solutions simply because I have logs in the original equation, and logs have a restricted domain. We never had to check our equations when we had exponentials because the exponential domain is all real numbers, so it doesn't care what your x value is, basically. So testing this in the two different domains that we have, one of those domains is x has to be greater than 0, because that's the entire input. The other one is x minus 1 has to be greater than 0. So checking the first one, 2 is greater than 0, so it works. The second one, 2 minus 1 is greater than 0, so that works. That's a solution. For our second one, if we just try it in the very first equation, negative 1 is not greater than 0. So if I try to plug this into the equation, the very first log is not going to be happy with that. So that is not actually a solution of this equation. All right, and last one. Again, same situation. The main difference is that this has a base of e. But once again, I can't move anything to the other side and just set the logs equal. So I'm going to do the same approach of combining the log equations together. This time, whenever I change it over to an exponential equation, it has a base of e. Now, in this case, it's definitely not factorable because e is irrational. So I'm not going to be able to just split an e into two different factors. So we are going to have to use quadratic formula. And because it's e, we're going to want to use our calculator to reduce it once we get the quadratic formula set up. All right, so my two solutions are 2 plus the square root divided by 2, and 2 minus that square root. So I'm going to solve each one using my calculator. Let's get that in focus. Let me zoom out a little bit. There we go. Okay, so first 2 plus square root 4 plus 4, and now e is on the natural log button, but it's in blue at the top, so you'll have to hit second and then natural log, and it's e to the power of 1. Divide that by 2. So one of our solutions is approximately 2.9283. And then we'll do the exact same thing, but this time with a minus. Yours will look much nicer because you don't have the ancient caret as your exponent in your calculator. Okay, so that one's negative. X is approximately negative 0.9283. So then we want to go back and double check our domains for both of these. The domain for natural log is the same as it was for log because they graph the same, the difference is the base. So x has to be greater than 0 and x minus 2 has to be greater than 0. So right away I can just say this is definitely not part of that domain on the first one. For the second one, even if we remove 2 from here, it's still positive, so this is a good solution. And if we wanted exact terms, we got that from doing 2 plus, so you would just write it as 2 plus square root over 2. All right, so that's everything. Sorry, this one was a bit long. Our homework for tonight is homework number 17, which should be posted at the moment that you see this video. And let's see, do we have a quiz? Okay, so next class we're going over some application problems. We do not have a quiz scheduled for next class. Also, the day after that is a review day for my white day because the orange day is SAT. So we're just not going to teach anything for half the class. And so the next time you'll see this information is on a quiz, which is on Thursday the 8th or Friday the 9th. That's the 19th day of our class. Okay, I'll see you guys then.